Okay, so this is the last video tutorial that you guys are going to get from me for Medi 304. So hopefully you found these somewhat useful in helping you remember what you need to report and how to do all the tests. So in this video we're going to cover repeated measures ANOVAs, two-way ANOVAs and ANCOVAs, and so they're the last things that we have to do. So firstly, let's look at doing a repeated measures ANOVA. And so we do a repeated measures ANOVA when we have more than 2 time points and we want to see the difference between each of those time points in a matched set. So in the context of this data set, we could ask the question, is there a difference in fat mass at baseline, week 6 and week 12? So that's 3 time points, these 3 right here. We want to see if there's a difference within them. Now remember, there is a non-parametric equivalent to the repeated measures ANOVA, which is the Friedman's ANOVA. If I was to decide which one to do, I'd have to do a normality test, which I hammered home very hard in the last video. So here we have fat mass at baseline, week 6 and week 12. I'll make sure normality plots with tests is ticked. And as we can see here, our data set is completely normal. If the data set wasn't normal, I would have to do the Friedman's ANOVA. So I'll show you quickly how to do a Friedman's ANOVA. So let's go to Analyze, Non-Parametric Tests and Legacy Dialogues, and we would go to K-related samples if we were doing a Friedman's ANOVA. And let's just say if fat mass was abnormal, we could put all 3 into this box and have Friedman ticked and press OK. And what you would have to report from this output is your chi-square value and your significance. But because this data was normal, we shouldn't have done a Friedman's test. I just wanted to show you on that data so you knew what to press. The important thing to note about all non-parametric tests, and the Friedman's test is included in that, is that we don't do post hoc testing when we do non-parametric tests. So that means that we've been told that there's a difference overall in this data set, but it's not going to tell us where that difference lies. So there's one benefit of parametric testing to non-parametric testing. All right, so to do the actual repeated measures ANOVA, we're going to go to Analyze, General Linear Model, and Repeated Measures. Here it asks for a within subject factor name. This is going to be time, because what we're looking at is difference over time. It's a repeated measures ANOVA. The thing we're repeating is time. So our number of levels is 3, because we have 0, 6, and 12 weeks. We're going to add that. Now we have to define it. So we have these question marks here, which indicates that SPSS wants us to specify something. So we're doing fat mass at baseline, fat mass at week 6, and fat mass at week 12. So those are our 3 measures. Now we can click on Options, and we can put time in the Display Means For box. We then need to click Compare Main Effects and Bonferroni. So remember, for a two-way ANOVA, repeated measures ANOVA, and ANCOVA, we're using Bonferroni. The only test we use a 2-key test for is the one-way ANOVA. I'm also going to click on Descriptive Statistics to get that one. You can also do a plot in the plot section if you wish, but for the sake of this test, I'm not going to. So that's all I have to do, and I'm going to press OK. And so you get a bunch of different outputs, and this is one of the harder tests to interpret. So we're getting our descriptive statistics. That's the same old that you've been seeing the entire way through this course. We have this box called multivariate tests. Ignore it completely. We don't want to look at this. What we do want to look at is the Morcley's test for sphericity. Now, the Morcley's test pretty much acts like a Levene's test or a normality test, but just for the repeated measures ANOVA. So what we need to see is if we get a significant value for Morcley's. So we can see here that our significance is 0.012, which is less than 0.05. This is a significant Morcley's. So this means the data does not fit this test for sphericity. Now, if the data was normal, I would then scroll down to tests of within subjects effects, and I would read all of my output from this sphericity assumed row. So I would report this degrees of freedom and this degrees of freedom. I'd report this F statistic and this p-value. However, because this is a not non-spherical data, it's a significant value, that means that we actually have to move on to the Greenhouse-Geiser correction. So what we can see here is that we have a non-significant result for Greenhouse-Geiser. So that means this one's all right to use, and we are going to now use this correction. So instead of reading from the sphericity assumed row, I'm going to read from the Greenhouse-Geiser row. So for my degrees of freedom, I will be using 1.679 and 72.197, with the F statistic 8.332 and P equals 0.001. So this tells me that over time, over the factor of time, there is a significant difference. So we know that there is a significant difference over the time, but between which time points? So that's something our Friedman's ANOVA couldn't tell us. But if we're doing parametric testing, we can figure it out. Because we did our Bonferroni post hoc, we can go down to this pairwise comparisons table, and it tells us the differences between times 1, 2, and 3, where time 1 was 0 weeks, time 2 was 6 weeks, and time 3 was 12 weeks. So if we read across the table, between time 1 and 2, there was a significant difference. So between 0 and 6 weeks, there was a significant change in fat mass. Between weeks 0 and 12, or time 1 and 3, there was also a significant change in fat mass. But the only one there is no significance between is times 2 and 3, which is greater than 0.05. So this means that there was a fat mass change between 0 and 6 weeks and 0 and 12 weeks, but not between 6 and 12 weeks. So those are the important values in a repeated measures ANOVA. So this one is actually going to be in the exam. So we've got to make sure that we can check our Morcley's test first. If it is significant like it is here, we use the Greenhouse-Geiser correction. If it isn't, we use the sphericity assumed row. We report this like we would a normal ANOVA, with F and then degrees of freedom in brackets, so 1.679 and 72.197 because this was significant, equals 8.332. P is less than 0.001. We then scroll down to our pairwise comparisons because we know there was a difference over time, and now we can say that there was a difference between 0 and 6 weeks, P equals 0.003, and 0 and 12 weeks, P equals 0.006. So the next test that we're going to look at is a two-way ANOVA. So a two-way ANOVA looks at two independent variables on one continuous variable. So we might want to say something like, is there an effect of gender and group on body fat percent at 12 weeks? So to do a two-way ANOVA, we will go Analyze, General Linear Model, and Univariate. We'll take this out of the boxes. So our dependent variable is our body fat percent at 12 weeks. And the difference between a one-way ANOVA and a two-way ANOVA is that we have two independent variables. So we need to put two things in the fixed factors box. So I'm going to put group and also gender. In the options box, I'm going to transfer all three of these variables into the display means for box. I'm going to click compare main effects and Bonferroni. Descriptive statistics is already ticked, so that's good. I'm then going to press OK. So here's our descriptive statistics for each group. And this is our test of between subjects effects. So this test is good for telling us three things. Is the group that our subjects were sorted into having an effect on body fat percent at week 12? Is gender having an effect on body fat percent at week 12? And the thing that the two-way ANOVA really answers is there an interaction between group and gender within this study? So that's going to tell us, is the group, as in the low, high dose or control, interacting differently depending on what gender the person within the group is? So potentially, the high and low dose groups might be working better for females. And if we got a significant result, we would know that there was an interaction occurring between females and the group they were sorted into. But that's not the case in this output. In this output, we can see that group, being our first independent variable, is not having a significant effect on body fat percent at week 12. Gender is having a significant effect on body fat percent at week 12. And for the group times gender column, there is no significance, which means there isn't an interaction occurring between gender and the group. And so then there's some pairwise comparisons. So for the group, there obviously wasn't any significance, so we don't need to look at that. And then for the pairwise comparisons between male and female, it does give us a significance value, 0.002. But that's the same significance value as here, because there were only two factors within the gender group, so we didn't need to look at the post hoc for that one. So the things that we need to report for a two-way ANOVA are, if the question asks for group, the effective group, we need to report the degrees of freedom for group and the error degrees of freedom with this F statistic and this significance value. If we're looking at gender, we need to use this degrees of freedom and this degrees of freedom, so 1 and 26, this F statistic, so 11.828, and this p-value, so p equals 0.002. And you would present this in the same way as a normal one-way ANOVA. So you would write F and then in brackets 1, 26 equals the F statistic 11.828, comma p equals 0.002. And then for the question, is there an interaction between group and gender? You would say no. Degrees of freedom 126. F statistic is 0.886. P equals 0.355. So the last thing we're going to look at is an ANCOVA. So an ANCOVA does the exact same thing that an ANOVA does, a one-way ANOVA, except it can account for what we call a covariate. So within this subject, a covariate is something that can influence your final results, and the majority of the time, it's a baseline score. So if we think about our leg press test at 0, 6, and 12 weeks, if I wanted to see the difference as a result of the group or the intervention, so the low dose, high dose, or control group, in the week 12 leg press scores, I could run an ANOVA. But I run the risk of then getting a result that isn't quite reflective of the reality, because when you think about it, these baseline leg press scores are going to be really varied depending on what kind of people are doing this study. We're comparing evenly the same people who had a score of 70 at baseline to the people who had a really high score, like 127 at baseline. Within this group, you might have people who are bodybuilders, people who've never been to the gym. And so, in reality, what we need to do is account for whether this variable is correlating to this variable. And if there is a strong positive correlation between the two, or a strong negative correlation, then we're going to actually be able to say with certainty that this variable needs to be accounted for when we're looking at the effect of the intervention. Because this change between 0 weeks and 12 weeks might not just be because of the intervention, it might be because of the natural strength that was seen at baseline with these people. So a question that wants you to do an ANCOVA will always ask you to control for baseline or adjust for baseline or take baseline into account. So to do that, firstly we need to correlate the bench press test or the leg press test at week 0 to week 12 to see if there is a positive or negative significant correlation. So we're going to go analyze, descriptive statistics, and explore, because the first thing we need to do is check that our leg press scores are normally distributed. So we'll put in leg press baseline and leg press week 12, and we'll make sure normality plots is ticked. So as we can see here, our leg press baseline score isn't normally distributed. Our week 12 is, but our week 0 is not, which means I'd have to do a Spearman's correlation rather than a Pearson's correlation. But I want to find a variable that I can do a Pearson's correlation on. So let's look at bench press score at 0 and week 12. So as I can see here, bench press baseline and bench press week 12 are both giving me Shapiro-Wilk values greater than 0.05, so my data is normally distributed. So for the sake of this test, I will now use the bench press baseline and the bench press week 12 scores. Remember, there is no non-parametric version of the ANCOVA that you need to know. So if you're asked to do an ANCOVA, your data is most likely going to be normal, and if it isn't, we will tell you that you can assume your data is normally distributed. So we're going to go analyze, correlate, bivariate, and we're going to put in bench press baseline and bench press week 12. We're going to tick Pearson's because we're doing parametric testing because these guys were normal. We're going to go OK. So what we can interpret from this box is that we have a significant, because P is less than 0.001, strong, very strong positive correlation between bench press baseline and bench press at week 12. So that means that this variable is having an effect on our bench press at week 12 score. So to do the ANCOVA to account for this, we're going to go analyze, general linear model, and then univariate. We'll get rid of these. So if I ask for the differences in week 12 as a result of our intervention or our treatment while accounting for baseline, my dependent variable is bench press at week 12, because that's the thing I'm really interested in. My fixed factors is my group or my treatment, and my covariate is my thing that I'm adjusting for, so our baseline bench press score. I can then go to options and put group in the display means for box, compare the main effects, and click Bonferroni. I can press continue and then go OK. And so there's two main things that you need to interpret from this output. Firstly, there's this baseline bench press row. This doesn't tell us anything about the significance of the overall test, because what we're looking for is there a difference in week 12 scores? what the baseline significance here tells us was that yes, this variable was having a significant effect on the results of the ANOVA, which is why we ended up doing an ANCOVA. The reportable row is this group row, because that's the row that is telling us, is group, low, high, and control, having a difference on my bench press score at week 12? So I would report my degrees of freedom. So I would go F1, 27 in brackets equals 3.409, P equals 0.076. So an ANCOVA was run to determine whether there was significant differences between our groups in their bench press week 12 scores. We adjusted for baseline as there was a positive significant correlation between the baseline and the week 12 scores. And after adjusting for this in an ANCOVA, it was found that there was no significant difference between our groups as a result of the low, high, or control treatments. So those are the 3 tests I wanted to cover in this video. So the important notes for this is that a two-way ANOVA looks at 2 independent variables on 1 continuous dependent variable. You need to be able to report your degrees of freedom, F statistic, and p-value like a normal one-way ANOVA. Our repeated measures ANOVA looks at the same group over 3 or more time points, and we're using a Bonferroni post hoc test for that one. The big thing about the repeated measures ANOVA is that your Morcley's test has to be non-significant for sphericity to be assumed. Otherwise, you use the Greenhouse-Geiser correction. And with the ANCOVA, you can test 3 or more groups whilst adjusting for a covariate. We adjust for a baseline score after we correlate the baseline to the week 6 or week 12 scores, whatever the question asks for, to determine if there is an effect being had. And then we will report the outcome the same way as a normal one-way ANOVA. So this is the last video in this series for your tutorials, and hopefully it's been helpful for your exam, and good luck and keep going on.